Hello everyone, I hope you're doing well and welcome to AliGorithm. In 1952, this mathematician called Claude Shannon made a remarkable presentation. As you can see, he presented the first mechanical mouse able to get out of a maze. Even though you won't be impressed watching this today, back then, some people got even scared from this mechanical mouse outsmarting humans described in Life magazine. Well, suppose you have a maze that you wanna solve. Indeed, using your own eyes and brain, you can look around and find a solution with this nice top-down perspective. However, suppose you have a larger maze, or even a larger and more complex one. Also, suppose you are placed inside the maze, meaning that you do not have this fancy top-down perspective where you can see the entire layout of the maze, but only your local surroundings. Well, to solve this, Konrad Zuse, with his signature eyeglasses, proposed a straightforward algorithm in his rejected PhD. Actually, his PhD was rejected by the university administration. He just forgot to pay the $200 inscription fee. Anyway, in this video we'll describe the most general maze solving solution, which is the breadth first search, or BFS. This algorithm is designed to work on graphs, aiming to discover their structure and moreover to find the shortest path and the distance from a start vertex to any other vertex. Consider the following graph. Roughly speaking, the BFS starts at a starting vertex, say S, and then discovers the graph layer by layer. This means it first visits the neighbors of S, then the neighbors of S, and so on until all the vertices of the graph are visited. Now let's describe it in details. The algorithm uses a well-known data structure called a queue. Like any queue, elements follow the FIFO first in first out protocol. Suppose they enter from the right and they exit from the left. The algorithm starts by marking the first node, S, then adding it to the queue with a label of 0 to indicate that its distance from itself is 0. Next, the algorithm extracts the top element of the queue, which is S. Once this element is extracted, the algorithm scans its neighbors, which are A, G, and H. These neighbors are added to the queue with a label equal to the label of the extracted element plus 1. That's 0 plus 1. To break ties, these elements are added in a lexicographical order. So the algorithm iterates like this. So by the end, a unique reversed path from any vertex to S is found. Considering T as example, a reversed path is marked, that is T, L, F, G, and S, encoding the S, G, F, L, T path, which is a shortest path by the way. Well, now let's discuss the complexity of the BFS. Let n be the number of vertices and m the number of the edges, or the arcs in case of oriented graphs. The algorithm iterates at most once on each vertex and each edge. So it's big O of m plus n in time and big O of n in space, as all of the vertices could be at the same time in the queue. Now back to our maze. This can be modeled adding a vertex to each pixel and an edge between pixels if we can move from one to another. As you can see, a BFS can be executed starting from the starting pixel. Finally, after discovering the network, a path is extracted in green, which is the shortest one, by the way. I hope you guys liked this video. If you have any question, please leave it in the comments below.